We'll get started. I mentioned I was going to try to get the next homework to you yesterday. Yesterday ended up being really busy, so I'm going to try to get that to you today. I'll make the same promise to you today that I made to you yesterday. Except I will really try to make that actually happen. I need to look at the schedule and see if that's going to be due next week or the following week. But that's, yeah, the upcoming homework. So you'll have it until at least Wednesday, as usual. But sometimes we get a little extra time in there, and I like to give people an extra week, especially for homeworks that are going to have pumping lemmas on them or something of the sort where I can. Depends on what we need to cover and what I need to make sure you have in by the time we take the next exam. But other than that, we're just soldiering on. Any questions before we dive back into CNF and GNF? And how we're going to use them to solve the membership problem? All right, we will get to it. So the first and more important of these two normal forms we're going to cover is CNF. And we might first want to figure out how to convert. Well, we first need to know exactly what it is, and then we need to figure out how to convert a general grammar into a grammar that is in CNF. So there can be two possible forms in CNF. One is a non-terminal arrow exactly two non-terminals. And the other is a non-terminal arrow a single terminal. And those are the only two production types allowed in CNF. As I mentioned at the end of yesterday's class, that means that we're trading off the expressiveness of one production for very simple productions, but we're going to end up with lots of those productions to make up for the fact that they are all extremely simple in nature. So go ahead and just as very quick practice, go ahead and write a grammar with at least 4 productions adhering to CNF. Make sure that all of your non-terminals are used in some capacity. And we'll start there. Something like this. That would be exactly 4 productions, but we can scale this as needed. But each of these adhere to one of those 2 forms, either non-terminal arrow, non-terminal, non-terminal, or non-terminal arrow terminal. And each of A, B, and C are defined somewhere. So there's no dead production, useless production, anything that we don't need. So the next thing we will actually care to discuss is how do we convert into CNF? And we guarantee that there is an algorithm that will allow us to do this as long as there is no lambda or productions with the right-hand side as a single non-terminal, something like A arrow B. And we talked last time about how to remove those kinds of productions from a grammar. So if you end up seeing a grammar like this, you can just go through these preliminary steps in order to get rid of these kinds of productions. So step one for converting into CNF, we're going to construct a new grammar from the grammar that we are given. And we're going to start by looking at all productions of the form where we have non-terminal arrow, some list of terminals and or non-terminals, which should be all of them. If the size of the list is 1, it must be a terminal, because if it is a non-terminal, then we did something about that in the preliminary step. In which case we can translate it directly into CNF. We don't need to do anything. Then we're going to introduce new non-terminals for each terminal in the production. We're just going to state that, all right, every single terminal now gets its own non-terminal. This makes sense because one of the possible rules in CNF is non-terminal arrow terminal. So we need some non-terminal that maps to every terminal. So for every terminal in the grammar, we just make a non-terminal that represents it. Now we're either going to have something, once we're done with this, we should have two possible forms of productions, either non-terminal arrow terminal, which is something that's already in CNF, or non-terminal arrow, a list of non-terminals in some capacity. So yes, no terminals in any production with the right-hand side length greater than 1. Makes sense? But now we need to reduce the length of these lists of non-terminals all the way down to eventually 2. So how we're going to do that is we just start to visualize each of these productions that is non-terminal arrow, a list of non-terminals. And we're going to break those down, introducing new non-terminals that represent most of that. All of that except for one of them, actually. So we just now make new non-terminals representing different subsections of that. And then we can construct new productions out of this such that the total number of non-terminals on each of these new productions is 2. This makes way more sense, I feel like, if you have an example, because this seems way more complicated than it actually is in practice. So any old production that is not in CNF gets removed at the end of this, and what you have is an equivalent grammar to the input in CNF. So let's go through an actual example. So we need to convert the following into CNF. Remember that there are only 2 possible legal rules here, a non-terminal arrow, non-terminal, non-terminal, and non-terminal arrow terminal. So step 1, we need non-terminals representing the terminals A, B, and C. So we are going to make those. So the first thing we should do is we're going to keep these current non-terminal names just to avoid ambiguity. I'm going to say that we're going to make a new non-terminal that represents A, lowercase a, another new non-terminal that represents lowercase b, and another non-terminal that represents lowercase c. And what I'm going to do from there is I'm going to back substitute the non-terminal for this back into these productions. So this new arrow is A, and the equivalent for C, which is E. Lowercase a, lowercase a, lowercase b is now C, C, D, and capital A remains. Lowercase b, lowercase a converts to D, C. And we can see at this stage, what remains is just either something already in CNF, non-terminal arrow terminal, or something that is a list of non-terminals. At this point, we don't care about these anymore. So now all we have to do is make some additional new non-terminals so that the size of these lists is shrunk down to 2. And the way we can do this is we can start a recursive procedure that just looks at every non-terminal except for the first one and groups them together into a new non-terminal. So we are going to make a substitution that says F arrow DC. And we're going to substitute back here DC for that new production F. We'll do exactly the same thing here, taking everything except for what's at the end, make a new production that represents CD. And back substitute here. And now we have a grammar that is in CNF. Each production adheres to those 2 rules, and we converted what was here into either 2 non-terminals or a single terminal. And note that we traded off kind of the hodgepodge that was these symbols, and we ended up needing more productions to represent the same idea. We have significantly more productions now, but those productions are very formatted using just 2 possible rules. And it turns out that having grammars in this form unlocks easier algorithms or possible algorithms to be able to do more complicated things in general with grammars. Any questions about the CNF conversion process?
Could we make non-terminals for groups of terminals? So could we
Yes.
have made A, B, one non-terminal? Okay.
Yes, you just do it recursively. It's like if we had 5 non-terminals in a row, you have non-terminal, group of 4 non-terminals that gets a description as a single letter. And then to break that down, you recursively say the first one and the last 3. And you recursively break that down to the first one and the last 2. And then that one's in CNF.
Oh, yeah, but I was asking about, so like for AAB, we've like the terminals, AAB.
Yeah,
Could we have made one non-terminal to represent that?
gotcha.
Like that?
Not
group of
easily,
terminals?
because then you wouldn't have a rule to expand to that would easily map to a CNF rule.
Okay,
You'd have non-terminal arrow 3 non-terminals, which isn't allowed in CNF, and we'll see why that will be a problem when we get to how we're going to use CNF.
okay.
So yes, you could, but it wouldn't be useful for how we're going to use this form. We need these 2 outcomes. We need each rule to be one that's exactly like this or exactly like. So, as usual, I've gone through all the steps of the slide without actually going through it, but here's an example of what you end up with. And again, we had options when we did this. I used the last 2 non-terminals. There's nothing that says you can't use the first 2 non-terminals and you leave the last one alone, or any other contiguous couple. Questions on the procedure before I erase and move forward? Feel like you could do this yourself on a homework?
Yes.
Right. GNF, on the other hand, I'll describe it. We're not going to go into as much detail on it because we're only going to use it in one translation process that comes up a little bit later. So we'll focus back on CNF here in a second. But 2 possible production forms for GNF, just like CNF. We can either have a single terminal, or sorry, all productions are in the form. There's only one possibility in GNF. All productions have to be a single terminal followed by 0 or more non-terminals. Every single production. So just like we did for CNF, go ahead and write a grammar for more production that's in GNF. Here's one off the top of my head. Any questions on GNF's form? Single terminal followed by zero more non-terminals, fairly straightforward. We end up using this when we want to convert between a grammar like this and the kind of automata that's going to represent this language class that we will discuss as soon as we're done with grammars. As we discussed regular languages, we went automata first, grammar second. And as we're discussing context-free languages, we're going grammar first, automata second. We'll see why that is. The grammars are actually a little bit simpler. All right, it's time to talk about the all-important membership question. This is probably fairly close to on par with the difficulty of the pumping lemma as one of the more challenging things we're going to talk about. And it is also your first programming project, which I will assign once we get through this. And we'll have a few weeks to do that before I make that due. But it actually is a reasonably challenging programming problem as well. And I think in what we're going to cover in this class, it tests your ability to put together a solution of something that you actually would want to show to someone. Some of these things would be simple enough. It's like, yeah, okay, you understand the basics, but this will actually show, oh, you know dynamic programming. Oh, it's a great example of a few more complicated CS programmatic procedures. So the membership question. Membership question is very easy in CNF. And as we discussed without CNF, it is exponential in complexity. We have to use brute force parsing, and brute force parsing was garbage. So once we have a grammar that's guaranteed to be in CNF, we can actually answer this in cubic time if we take advantage of dynamic programming. So what we're going to do, we need to define strings as made up of a set of characters. So lowercase c followed by a subscript is going to be the position of the character in the query string. Then we also need to be able to talk about what is the substring between positions I and j. So that is going to give us w sub ij, and these are going to be inclusive. So this isn't like the substring method in Java that goes up to but not including the last number. This is going to be inclusive. So if we say w11, we're looking at a single character, the first character in the string. This is not zero indexed either, this is one indexed. Finally, we're going to define capital N sub ij as the set or subset of left-hand side non-terminals in a grammar in CNF that can produce that substring, w sub ij, via some sequence of productions. So going through that left-hand side, right-hand side, expanding that out into something, we could eventually create that substring. And it turns out by storing this table, we can answer the membership question. So this is going to turn into a table for all such I and j. If we can answer the n sub 1n question, so the productions that can produce the entirety of the string, and the start non-terminal is in that set of productions that can produce that, that is the answer to the membership question. If we can go S arrow some crazy amount of work, arrow W, the entirety of the input string, then we know that S can produce W. If it was impossible via some sequence of productions to produce W from S, then W is not in the language of the grammar that is specified. Do we agree that that is the membership question? It's just a matter of what happens here to produce this. So that is the question that we're trying to answer. It's just that now we have a single question that is not easy to answer. What is n sub 1n? And it turns out that that is a series of questions that break down into n sub a bunch of ij's that are lookups, and each of those break down into n sub ij's that are sub lookups of that, and it breaks down to the point where we need every cell in this table filled to answer one of those queries. So we are going to procedurally fill that table using the results that we store in order to calculate additional cells, using that information to calculate additional cells, using that to calculate additional cells. And in case you haven't seen or need a refresher on dynamic programming, that's exactly what dynamic programming is. You're using subproblems and building up solutions via stored solutions to subproblems. And that is way easier than brute force asking this question recursively and breaking it down. So who's seen dynamic programming before? Just about everybody. Who has a great intuitive understanding of dynamic programming?
It was a long time ago.
Long time ago in a galaxy far, far away. It sounds like a great Star Wars sequel. I mean, they've already ruined them. Might as well turn it into a dynamic programming lecture at this point.
Yeah. Did you ever hear the tragedy?
Yeah.
Dynamic programming.
Doth dynamic programming. The why.
Darth Greibach.
Sounds like
Why is it that all of these scholars sound like Sith Lords? They all got these crazy European names.
Yeah. Yeah.
Chomsky.
It's funny what happens when we fund education, isn't it? All right, so I'm going to give you an example of dynamic programming, just to kind of visualize this because it's useful to see. We're familiar with the Fibonacci sequence?
Yes.
Yeah, so recursive definition, the sum of the two numbers prior to it in the sequence define it, with the first two numbers being 0 and 1. So sum of 0 and 1 is 1, sum of the prior two, 1 and 1, 2, 1 and 2, 3, 2 and 3, 5, 3 and 5, 8, etc. So the dumb way to do this is recursively, if I give you a query of what is Fibonacci of 7? I'm just going to write this as 7. I kind of just want a little bit more space. So this is going to go away for a moment. Fib of 7 can be broken down into fib of 6 and fib of 5. We can't answer either of those directly if we start with fib of 7, so we have to break each of them down into fib of 5 and fib of 4. And 5 becomes 4 and 3, and 5 becomes 4 and 3, and 4 becomes 3 and 2, and 4 becomes 3 and 2, and 3 becomes 2 and 1. Do we see how this starts to be a problem? We're repeatedly calculating the same thing over and over and over and over. And you can imagine if this wasn't Fibonacci of 7, because I wanted to fit most of this tree on the whiteboard, if I asked Fibonacci of 1,000, there would be exponentially more and more work as we got farther and farther away from the initial query. We asked 7 once, 6 once, 5 twice, 4 3 times, 3 1 2 3 4 times, 2 1 2 3 4 5 6 times. It gets more and more and more and more and more and more and more as you go. A smarter way to do this is to calculate Fibonacci of 1. Wherever we see Fibonacci of 2, use the looked up value rather than recalculate it. Once we have Fibonacci of 2, use that wherever we're calculating Fibonacci of 3. So if we stored a table, and we just stored 7, 6, 5, 4, 3, 2, 1, before even considering the right-hand side of this tree, we end up with just kind of a list that goes depth first down that tree. Fibonacci of 7 breaks up into 6, and I'll actually write 5. Recursing on the left subtree, this becomes 5 and 4. Recursing on the right side, left side, 4 and 3, 3 and 2, 2 and 1, 1 and 0. And sure, we'll include 0 because we know these answers right away. We define this to be 0 and we define this to be 1. So we can now calculate Fibonacci of 2. When we calculate it for the first time, we store it. 1 plus 0 is 1. When we calculate 3, it's a lookup to 2 and 1, which we both have. 1 plus 1 is 2. So now when we calculate Fibonacci of 4, we just have to look at 3 and 2. we can see how this doesn't use any more space or any more of this tree than just something that is linear in nature. So we've taken what was going to be an exponential complexity problem, calculating something for every position in this tree, where every level of this tree is twice as large as the last level, and involved repeated looked up calculations. And now we just have to fill out a linear sized table via a what looks like kind of a linked list with a little friend that it carries along with it. And that is way easier and way less time as this scales past 7 and goes to 100 or 1,000 or 10,000. So if you can intelligently think of the problem that you would want to solve from the top down as solving it from the bottom up, and store the information as you go, such that when you come to a problem, it's always lookups in the table of something you've calculated before, then you end up with a much more efficient solution, and you can solve much larger aspects of that problem in the same amount of time. So that's just the general idea of dynamic programming. Whenever you can come up with a data structure, allowing for stored calculations to avoid repeats. And for some reason, dynamic programming is taught in a way that's way scarier than that, and I don't understand it. That's all it is. So we're going to see that this is an exact, perfect avenue to apply that idea, just in one more dimension. So to answer the question for n sub I, let's first envision this as kind of a table. Do I want to do that, or do I want to go wait for an example? I probably want to wait for an example, so I actually draw out the right table. But we want to start with, it's going to end up being another diagonal table or triangular table. And we're going to start by answering n sub I, which is a really easy question to answer. It's just a lookup into the CNF grammar. Because to be able to produce a substring of length 1, the only productions that can produce a substring of length 1 are the productions of the type non-terminal arrow terminal. No other production can produce a single terminal, since they all have to lead to multiple non-terminals, and each of those non-terminals has to lead to at least one terminal. So the only way to produce a single non-terminal is via a single production with that form. So we can answer the entire first row of this table, n sub I, for every I, the index into the string, index 1, 2, 3, 4, up to index however long W is. So we look up for a grammar of some form, non-terminal arrow, that character, and that becomes the subset that can produce n sub I. And we're going to write down the left-hand side of that production in that cell. As we start to go ij and start to answer the W sub ij, N sub ij problem, we end up being able to find some k. We're going to look at every possible midpoint in that substring and try to break it down into a recursive process of what generates the left-hand side of that string and what generates the right-hand side of that string. And at that point, both of those will be lookups in the table. So if we want to find what is n sub 1, 2, this represents W sub 1, 2, which is the first two characters in the string, starting at index 1, ending at index 2 inclusive. If we have that string, maybe it's, the first characters are A, B, and we want to figure out what subset of productions can produce A, B, then we can split this in half and say, all right, well, this is just what production can produce this and what production can produce this. So let's say in the grammar, there is some A arrow A and B arrow B. That means that if we combined these together, the production AB would be able to produce this. And if we have some production that does this, we see that a left-hand side, right-hand side is the other form of an allowed production in CNF. So we're going to break this down into the non-terminal that can generate the left-hand side and the non-terminal that can generate the right-hand side. And that's going to map to 0 or more right-hand sides of productions, for which we're going to write the left-hand side of that production in our table at the cell n sub ij, where it breaks down into a left-hand side ik and a right-hand side kj. I know that's a lot. It'll make much more sense with an example, I think. Any questions on this general idea that I can answer at this point?
So the entries in the table are the non-terminals that would produce what was seen
Yes,
at those coordinates, and the coordinates are the position of the cell where we wrote the non-terminal.
yep,
Okay,
that's basically right. So yeah, this is gonna be a list of left-hand sides in the table. And those left-hand sides, when combined, are going to allow us to see additional places in the table further up. And the very last thing we're going to answer is the query, the entirety of W, from 1 to the length of W. And what we're looking for is the start non-terminal in that set? But we have to end up looking for every k between I and j to do that. So it gets to be a bit of an annoying process for longer strings. This is why it is cubic in nature. We have a number of columns equal to the number of characters that are the length of W. A number of rows that's the same, because we have to consider strings of length 1, 2, 3, 4, up to strings of length the entire thing. That's why it ends up being triangular. And then the third dimension is for all k in between that. This will make way more sense as we draw it out. So to proceed, I'm giving you the name of the algorithm. CYK is what you will be implementing for your programming project, and writing out in some homework and some nice problems and some less nice problems. So first thing you'll do is fill out the first row of this triangular table. So compute all possible n sub I, which means 1, 1, 2, 2, 3, 3, 4, 4. These should all be direct lookups in the grammar from production's non-terminal arrow terminal. Then you fill out the second row, which is all possible n sub ij, where j minus I is 1. So 1, 2, 2, 3, up to the length of WL. Then you get L minus 1 L. Then you look for the next row, difference 2. J minus I is 2. 1, 3, 2, 4, up to L minus 2 L. And continue all the way until you have n sub 1 L, which is the entirety of the string W. This is just kind of the logical way to think about it, and I think most people will attach themselves better to the example that's coming on the next slide. See if I can do this in 15 minutes. If not, we'll come back and finish it off tomorrow. All right, so here is a very fun grammar that we will come to know and love that is already in CNF for us. So you can imagine having gone through a conversion procedure, converting this into CNF. We are going to say that the string that we are curious about is AABBB. So this tells us already the table that we need to make. And again, I'm going to shorthand the slides and just do this all and reveal it at the end, because this gives me a little bit more space. So I'm going to draw this table more like this. We're going to have, we need space for the first, the second, the third, the fourth, and the fifth. We need space up to here. We need space up to here. Space up to here. And the very last query. So the answer is going to be here. But we cannot fill out that cell until we fill out every other cell. So this represents n sub 1, 1. This is n sub 2, 2, n sub 3, 3, n sub 4, 4, and n sub 5, 5. What we have here is n sub 1, 2 up to n sub 4, 5. From here, we have n sub 1, 3 up to n sub 3, 5, n sub 1, 4 up to n sub 2, 5. And finally, we have n sub 1, 5, which is the entirety of which production can produce the query string, which 0 or more productions can produce the query string from the baseline. So the middle cells here are labeled as well. I'm just kind of giving you hopefully a sense of what each of these cells represent, what the rows represent, what the columns represent from some of these labels. And this is position 1, 2, 3, 4, and 5 in the string. So the very first question is to fill in this cell, n sub 1, 1. This says which productions in this grammar can produce the substring starting at position 1 and ending after position 1. So this is A. The very first A in this string. Is there a production over here that can directly produce that character, A? What is the non-terminal that can produce that? Be able to produce the A?
Okay, A.
Is the A, yeah. So each of these are sets. And it is the set of all left-hand sides, the non-terminal that can produce the string that is on that right-hand side. So A can produce that. N sub 2, 2 is just looking at the second character in the string, which is also an A. So it goes in that cell. It's just a set that contains A. N sub 3, 3 is looking at the third character in the string. On our right-hand side, we're looking for that character. What is the associated left-hand side that can produce that character? Anything that can do that goes in this set. Same thing for 4 and 5. The first row is easy. The second row is a little harder. So the second row states we're going to look at the substring starting at position 1 and ending at position 2. So that is going to break down into AA. We now need to break this in every possible middle point, where we have a left-hand side and a right-hand side. But what we know about the positions of these is that they're already lookups into this table. So here, this left-hand side is a lookup to n sub 1, 1. Because this is position 1 in the associated string. The right-hand side is a lookup to n sub 2, 2, because it is a position representing that. So we're going to break this down and say A is the only thing that can produce the left-hand side, what is in this table. A is the only thing that can be produced on the right-hand side from this table. So we're going to end up taking the cross product. These are going to end up being sets. But we need to take the cross product of those sets. This allows for everything on the left-hand side, everything on the right-hand side. So tuples that are something from here, something from here. Well, as this starts to have more things in it, we'll start to see what that actually is. But what this means is this produces the tuple AA. As a result, and it's a tuple of a set of tuples of size 1. So we're looking for AA somewhere on the right-hand side of a production. Is there a capital A somewhere on the right-hand side of a production? No, there is not. So this is the empty set. Does that make sense? So the left-hand side of this is a lookup to n sub 1, 1. The right-hand side is a lookup to n sub 2, 2. We take the cross product of these two sets to produce a set of tuples. And then we look for anywhere that any element of these tuples appears on the right-hand side of a production. And this is always going to be length 2 in tuples. So we're always looking up to productions that are of the form, the CNF form, non-terminal, non-terminal on the right-hand side. So the first row is looking at productions of the form non-terminal, arrow, terminal. Every other row is looking for non-terminal, arrow, non-terminal, non-terminal. Let's continue. The next cell, n sub 2, 3, is going to bring down that substring AB. We think about everywhere to divide this, that creates a lookup. This is n sub 2, 2, which is the set containing A. On the right-hand side here, we have the set containing B, a lookup to n sub 3, 3. Taking the cross product of those gives us a set of tuples that is size 1, AB. Looking on the right-hand side, do we have any production that can produce AB on the right-hand side? We have two of them, S and B. So this set is going to contain two elements, S and B. Because both of those left-hand sides can produce the AB that is this tuple. Continuing. The next substring we bring down is BB. Looking in the middle of this, we're going to have lookups to n sub 3, 3 and n sub 4, 4, which is going to end up being BB. Anything on the right-hand side that produces BB? A does. So that is what we write here. What's nice is this is exactly the same thing for the next one. You can see that the lookup for n sub 4, 5 is going to be exactly the same BB that we would bring down. It just is a different portion of the string. But we look at B and B here. It's the same as B and B here. What produces BB? The same thing, A. We move up a row, and it gets harder. We're going to bring down the substring 1, 3, which is A, B. Now there are two possible middle points. So I'm going to duplicate this string and split it here and split it here. This here is looking at n sub 1, 1. This here is looking at n sub 2, 3, right? Since we're taking, this is starting at position 2 and going up to position 3. We're going to take the union between these and split this up into AA, which is n sub 1, 2, and B, which is n sub 3, 3. So each of these are going to create cross products. And then we take the union of the sets of tuples in that to be able to generate whatever we need. So n sub 1, 1 is A. So we have A cross n sub 2, 3, which is here. What's n sub 1, 2?
Empty set.
Empty set. What is the empty set cross anything? The empty set. So I'm going to stop worrying about this. I can stop early because there will be no possible tuples made out of this. So this carries down to just become the empty set. But the cross of A and S and B produces two tuple elements. We have AS and AB. Anywhere on the right-hand side that has either AS or AB?
S has AB.
It is, yeah, S does and B does. So the union of all of this is S and B. And that's what we write here.
There's a lot to keep track of this stuff, but this is gonna become a dynamic.
Yes, this is why we code it.
I can already tell that it's real fast.
This is why we have computers. When things get annoying for us as people, delegate. Delegate to things that don't have feelings. Like students.
But it's nice though, because I think that you're kind of explaining it, at least from what I'm getting out of this. You're kind of explaining it how the computer's gonna do it.
Yeah. I tend to have an algorithmic mind, so I like to think of it in terms of how would I break this down into its associated subproblems that you can just assign method names to and write it in terms of a method.
When I'm writing this, I'm probably gonna watch this lecture. Like,
So here's everything we need to consider to fill in that box. How do things change for the next box? Well, we just have. Just erase the whole thing. We have ABB. I'm duplicating it once because there are two possible splits here and here. So this A is that A, which is n sub 2, 2. I'm just going to start writing 2, 2 and 3, 4. Here we have 2, 3 and 4, 4. We agree that those are the indices of the two substrings. Two minutes. So 2, 2 is a lookup to here, which is A. 3, 4 is a lookup to here, which is also A. We're going to union that with 2, 3, which is SB, and 4, 4, which is B. So it's AA union SB, BB. Is there any AA on the left-hand side or right-hand side of a production, SB or BB? The union of all of that has just BB, which is coming from production A. And that's it. No other right-hand side produces any of that. Any questions on that work so far? Yeah.
can you explain again how you got SB on the previous one?
Yeah, it's a lookup to n sub 2, 3, which is going to be this cell right here. So we have the column is the first number, 1, 2, 3, 4, 5. And then the row is the difference between the numbers. So because we have 3 and 4, that difference is 1. That tells us we're going to be in row 1 if this is 0 indexed. It's annoying to me that the columns are 1 indexed and the rows are 0 indexed, but that's kind of how I fairly quickly look up where that's going to be. So n sub 2, 3 is if this is 1, 2 right here, then this is 2, 3. So you take every element of that set, cross product, union. Look on the right-hand side, determine all of the productions on the left-hand side that could produce that, and then fill that in. All right, unfortunately, we're out of time. I have to call it here for the moment. Someone hopefully has taken really good notes and can help me construct this in a fairly quick amount of time so that we can continue where we left off. I'll go over a couple more of these, just like one or two of these, and then fill out the rest of the table, just to make sure that we're hop back up to it at the start of tomorrow's class. And I will try to get that assignment to you at a reasonable time early this afternoon. Yeah. All right, thanks everyone.
Which is homework 3 out.
Not yet, trying to get it up by this afternoon.